Good afternoon. As announced before, today I will prove the Hopf-Reno theorem, which says that if S is a connected complete regular surface, then there exists a minimizing geodesic segment between any given pair of points of S. So let P and Q 2 points of S and set R to be the intrinsic distance between P and Q. Let C to be the distance circle about P of radius epsilon smaller than R and small enough to ensure that C is contained in a normal neighborhood of P. C is a compact set because C can be seen as the image by the exponential map at P of a circle. Let's write this way, circle of radius epsilon in TPS, and by continuity of the exponential map, then C is compact. We will also use the fact that the distance to Q function is continuous this is an exercise. I will not solve the exercise today. This implies that if I consider the restriction of this function, I mean this function here, attains a minimum at a point that I will call X. So in other terms, if this function attains the minimum at x, this means that x is the point of C, which is closest to Q. Now let V the vector in TPS of length 1 the vector tangent to the unique minimizing geodesic from P to X. Since the radius of C is equal to epsilon and the X belongs to C, then we have the following fact. The unit speed geodesic gamma defined on 0 plus infinity. This is possible because the surface S is complete, defined by this formula. Satisfies gamma 0 equal P and gamma epsilon equal X. Let's make a picture. So this is the point P, for example. This is the point Q. The distance between P and Q is equal to R. And we chose a distance circle centered at P of radius epsilon smaller than R, and chosen small enough to ensure that C epsilon, that for example is this one, C equals C epsilon P, is contained inside a normal neighborhood of P. This is why we are sure that if we work with points contained inside this disk, there is a minimizing geodesic from P to those points. So we said that X, which is the closest point to Q, is connected to P by minimizing geodesic. For example, we use the blue color. This is X equal gamma epsilon what is our goal? show that gamma r equal q. In other terms, we have to prove that if we travel along this geodesic, the geodesic joining P to X, we hit the point Q. The idea of the proof is the following. Set U to be the values of the parameter t in epsilon r such that the distance between gamma t and q is exactly r minus t. We have to show that u coincide with epsilon r, and if we do this, we have that gamma r is equal to q, because if we replace r into this formula, we get intrinsic distance of gamma r q equals 0. So our goal is to prove this identity. Okay, in order to prove that this is true, we have to show three things. One, U is non-empty. Two, U is closed in epsilon r. 3, U is open in epsilon r, and using the fact that epsilon r is connected, then we have that U is equal to epsilon r. Okay, let's prove one. We will show that epsilon is a point of U, and this implies U non-empty. Maybe it's a good idea to copy the definition of U here. U equal T in epsilon r such that the distance gamma T Q is T minus r minus T. The idea for proving that epsilon belongs to U is that every curve in S between P and Q must intersect C. So we can write the following formula. R, the distance between P and Q. This can be written as the infimum of the sum of the distance between P and Y plus the distance between Y and Q with Y in C. So in other terms, I'm considering curves joining P to Q and passing by a point Y in C. For example, in this case, Y is this point here. And I'm saying that the intrinsic distance between P and Q is the infimum of this sum. But the infimum of the distance from P to Y is epsilon because Y belongs to C. And the infimum of this distance is the length of minimizing geodesics joining P to Y. But Y is a point, the distance epsilon from P. So this is an infimum of epsilon plus the distance of Y to Q with Y to C. But let's now use the fact that X is the closest point to Q. So the infimum of this distance is epsilon plus the distance of X to Q. What we proved? We proved that the distance of gamma epsilon Q, that is the distance of X to Q, is equal to R minus epsilon This implies that epsilon belongs to U. Why? Because I proved that the distance of gamma epsilon to Q is R minus epsilon. Now let's prove that U is closed. So U is closed follows from the fact that gamma T is a continuous map and the distance to Q function is continuous. So if you have that T1, T2, T3 is a sequence of numbers with Ti in U, then if limit of Ti as I tends to infinity is at T bar, then T bar belongs to U, because the image of a convergent sequence by a continuous function is convergent. So the fact that B gamma Ti Q equal to R minus Ti implies that the distance gamma T bar Q is R minus T bar. So this says T bar belongs to U. Now we have to prove that U is open. So proof of 3. So suppose that T0 is in U and T0 is more than R. Set C tilde to be the distance circle of radius delta about gamma T0 with the delta smaller than R minus T0. This is small enough to ensure that C tilde is contained in a normal neighborhood of gamma T0. So let's make a picture. This is gamma T0, for example, and this is C tilde equal C delta gamma T0. C tilde compact implies there exists y in C tilde which is the closest point to Q. So we have Y, for example, this one. Y, we forget this Y, we don't need it anymore. And by definition of distance circle, we know that this distance here is delta. Our goal show that Y is gamma T0 plus delta. So in other terms, Y is not this point here, but is this one. Okay, suppose by contradiction that this is not true. And if this is not true, we can use the same argument applied before when we proved that epsilon belongs to U and U is non-empty. So let's say same argument as before, same argument as before, implies that the distance between Y and Q is R minus T0 plus delta. Now we can use the triangle inequality to estimate the distance between P and Y. The distance from P to Y is larger or equal to dpq minus distance between Y and Q. The first one is R, the second one is written here. And this is T0 plus delta. So this means that the distance between P and Y is larger than T0 plus delta. And this formula says that the distance is obtained by a non-smooth curve. Why? Because let's give a look at the piece of geodesic joining P to gamma T0. And the piece of geodesic joining gamma T0 to Y. This second piece of geodesic exists because C delta is contained in a normal neighborhood. But this is a contradiction because a minimizing curve in this case the curve given by the union of this geodesic and this geodesic cannot be a geodesic, cannot be non-smooth. This fact is proved in an exercise and we will prove it later. So since we reached the contradiction, we have that y is equal to gamma t0 plus delta, and the distance of y to q is r minus t0 plus delta. This says that t0 plus delta belongs to u. So we proved that we proved the following fact. We started with t0 in u, and we proved that the t0 plus delta is in u with delta positive. So if this is t0, we prove that a right neighbor of t0 is contained in u. What about the numbers between epsilon and t0? So every number between epsilon and t0 belong to u. Why? Because if you consider the geodesic, okay, let's say this way. If you know that a number belongs to u, then it's easy to prove that any small number belongs to u. Just consider a geodesic starting at, for example, gamma t0 and joining gamma t0 with gamma t prime. And you can prove that distance of gamma t prime q is r minus, sorry, t prime, r minus t prime. So we prove that a neighborhood of T0 is contained in U implies U is open. And this is the end of the proof. Next topic of today is the parallel transport and the covariant derivative. Let's start with this definition. So let S be a regular surface and let gamma be a regular curve in S. Let V be a vector field along gamma that is a smooth function V defined on an interval I, the same interval I used in the definition of gamma, with values in R3 such that Vt is a vector in T gamma T S for all T in I. And the definition I need in the sequel are the following ones. The covariant derivative of V denoted by dV dt or dTV or VO prime. Please observe that in other textbooks only these two notations are used. This is instead non-standard. Is the vector field along gamma defined as follows. For all t0 in I, dv dt at t equal t0, this is a projection of v prime t0 onto t gamma t0 s. In other terms, the covariant derivative is the projection onto the tangent space of the usual derivative. Second definition I need, V is hold parallel if dv dt at t equal t0, this is 0, where 0 means 0 vector, for all t0 in I. The next result, lemma 5.39, lists the algebraic properties of the covariant derivative. So let VW be vector fields along gamma, and let AB be smooth functions with values in R. So we have the following: 1 V plus W O prime is V O prime plus W O prime. Now I'm using the non-standard notation. 2 A times V O prime equal A prime V plus A V O prime. 3 ddt of V inner product with W. This is the inner product of V O prime V, W plus V inner product O prime. Excuse me, V inner product W O prime. For if phi is a map between two intervals, which is smooth, then V tilde equal V component phi, is a vector field along the curve gamma tilde equal gamma composite phi, and we have that VO prime t is equal to phi prime VO prime of phi t for all t in I tilde. In other terms, if you have a reparametrization of a curve, then how to construct a vector field along this new curve if you have a vector field along gamma? Just take V tilde equal V composite phi, where phi is the reparametrization. If you want to prove this formula, you just use the fact that these formula are true for the usual derivative, and then you can project, then you can consider the projection of the vectors onto the tangent space. That is, you replace the symbol prime by O prime. What are the consequences of these properties? Let's recall for a moment the definition of parallel vector field. A vector field is parallel if VO prime is 0 everywhere. So one says that VW parallel imply V plus W parallel. Why? Because if this is 0 and this is 0, the sum is 0. 2, V is parallel if and only if, if V is parallel, then AV is parallel if and only if A is constant and why? Because AV is parallel if this derivative is 0, and this is 0 if both of these terms are 0. This is 0 if V is parallel, and this is 0 only if A prime is 0, which means A is constant. Consequence of 3, a parallel field has a constant length. How to prove this? Take V equal to W, then you get the square of the length. The derivative of the square of the length is 0 if the vector field is parallel, that is, these two summands are 0. Second consequence of the same formula, two parallel vector fields maintain a constant angle. In order to prove this statement, you use the fact that if the parallel vector fields, if the vector fields are parallel, then this is 0, and consequently this derivative is 0, but this is length of v, length of w, cosine of theta, with a sign, a symbol of derivative in front of it. This is constant because it's written here. This is constant, so to make this 0, we need that the cosinus of theta is 0. This means that the angle is constant. Consequence of 4, statement number 4 is written here. V tilde equal V composite phi is parallel along gamma tilde if and only if V is a parallel along gamma. This follows from this formula. If V is parallel, this is 0, then this is 0. I made a typo. This is V tilde, excuse me. So V tilde O prime is 0 because this is 0. Now I want to prove the following theorem. The existence and uniqueness of parallel vector fields. This theorem answers the following question. Suppose that we have a regular curve gamma on a surface S. Suppose that you want to construct a parallel vector field along gamma such that let's call it W, such that WT0 equal W0 for T0 in I, where I is the interval of definition of gamma, and W0 is given. Is it possible to construct this vector field? The answer is yes. And the construction is unique. So we have that for every W0 in T gamma T0S, there exists a unique parallel vector field W along gamma such that W T0 is W0. How to prove this result? Okay, let's assume that gamma is of unit speed and W0 as a unit length. We can do this because lemma 5.31 holds true precisely if we want to work with a curve which is not of unit speed, just consider a reparameterization of it. And if we want to work with a W0 which has no unit length, just multiply it by a constant. For simplicity, we will assume S oriented. Then we set V to be gamma prime, and we observe that N equal R90 of V is another vector field of length 1 along gamma. Why? Because this has length 1 by hypothesis, actually by assumption, and R90 is the rotation by 90 degrees in the counterclockwise direction with respect to the orientation. The first step of the proof consists in proving these two formulas. VO prime equal geodesic curvature times n, and NO prime equal minus Gauss curvature times V. This looks like the Frenet equations which holds true for plane curves. How to prove the first one? To prove the first equation, let's look at equation 4.8. This says that the acceleration of a unit speed curve on a surface can be written as Kn n at p plus Kg R90 V. It's enough to consider the projection of this equation in the direction onto the tangent space. This means that this term here disappears, and A, which is V prime, is replaced by the covariant derivative, and from this formula we get immediately that it is equal to Kg times n. How to prove the second one? So n as a unit length implies NO prime comma n is 0. You can prove this as you do for the formula n prime comma n equals 0. Same proof as this one. Since this is true, then n prime is parallel to V. Why? Because we define n to be the rotation by 90 degrees of V. So if a vector is orthogonal to this one, then it's parallel to this one. How to find the component of NO prime along V? It's simple, we use this formula. We proved this formula before, and this is equal to 0 because they are orthogonal, and this value, the value of this product follows from this formula here, and it is equal to Kg. And this is the proof of this formula. Okay, so now we want to construct a vector field W parallel along gamma such that Wt0 is W0. We define Wt this way: cosinus of theta t Vt plus sinus of theta t times n of t. We want this to be parallel, so W is parallel if and only if W prime is 0. W prime t can be determined computing the covariant derivative of this vector field, and when we compute this covariant derivative we use these two formulas, and again lemma 5.39. If we do this, we get that this covariant derivative is minus sinus of theta times theta primes plus kg Vt plus cosinus of theta times theta prime plus kg n of t. So this is 0 for any t in I if and only if these two functions are 0, and this is true if theta prime plus kg is 0, that is theta prime equal minus kg. The solution of this equation is theta prime t equal a certain constant minus the integral from t0 to t kg s ds, where this constant here is determined so that W at t0 is W0 as written here. The solution to this equation is unique. It follows from the fact that theta t is unique once we determine theta 0. The next definition I need in the sequel is a definition of angle function. So as usual, we have our regular surface, and in this definition we require also that it is oriented. Gamma a unit speed curve in S, and kg the geodesic curvature function. Let theta, the function defined on I with values in R, be an anti-derivative of kg. So this means that theta prime is kg. Then theta is the angle function of gamma. It is unique up to an additive constant, and enjoys the following property: for every unit length parallel vector field W along gamma, there exists theta 0 in 0 to pi such that gamma prime t equal cosinus of theta t plus theta 0 wt plus sinus of theta t plus theta 0 R90 wt. So this definition says that the velocity vector of a curve can be written as a linear combination of wt and R90 wt, and the corresponding coefficients are the cosinus of theta t plus a constant and the sinus of theta t plus a constant. Next definition I will use later. is a definition 5.45, part 1. So let S be a regular surface, and gamma a regular curve in S. Then the parallel transport along gamma is the function let's write it here, P gamma T gamma A S T gamma B S. So is a map defined on the tangent space to gamma A with values in the tangent space to gamma B, and it is defined in the following way. Define to send W0 in T gamma AS to the value at T equals B of the parallel vector field along gamma whose value at T equal A equals W0. So in other terms, let's try to make a picture. If this is gamma A, this is gamma B, and this is W0, and this is a vector field a parallel vector field W such that WA is W0. Then P gamma of W0 is W of B. The P is vector here.